So to start out this new chapter, we're going to talk about antifreeze. So antifreeze is a problem because it's ingested sometimes by animals and other wildlife. And it's a problem because, antifreeze has ethylene glycol in it. And ethylene glycol has a sweet taste and can make you feel a little bit tipsy. So initially, you might feel like nothing's wrong. But when it gets metabolized in your body, it turns into glycolic acid. And glycolic acid is this molecule here that can actually react with the bicarbonate ion in your blood, causing your pH to drop. So since it's acidic, right, it's an acid, it's going to react with this, the bicarbonate ion, which can act like a base. It's amphoteric because it has a negative charge. It can act like an acid or a base. Acid if it donates a hydrogen, or a base if it takes a hydrogen on. So the glycolic acid will react with the bicarbonate, which is buffering your body's blood, keeps the blood at a really great pH. But if your bicarbonate gets all used up, then you're going to have too much glycolic acid. And so this makes it hard for your body to carry oxygen around in your blood, and that's called, when you can't carry oxygen, that's called acidosis, when your pH is so low that you can't carry oxygen. So we have this reaction here where hemoglobin, which is proteinized by being really high oxygen, is unable to pick up the oxygen, and so we have a shift in our equilibrium here, so we're not able to actually have oxygen in the blood. And one way to solve this problem is to give patient ethanol or ethyl alcohol, which can basically bind to an enzyme that catalyzes the ethylene glycol. So basically prevents that from forming into glycolic acid. So got a little bit of kinetics in here, as well as some intermolecular forces, as well as equilibrium. So now we're going to talk a little bit about what buffering is. Before we talk about a buffer, we want to talk about this thing called the common ion. And we've actually seen this before with our polyprotic acids in the last chapter. Basically, if I have an acid solution, right, I have, in this case, acetic acid, weak acid, it's going to make a little bit of hydrogen and a little bit of acetate. But because it's weak, it's only going to partially dissociate. Remember, our K is less than 1, so we have a lot of reactants. Okay, now if I put sodium acetate in water, it's going to completely dissociate because it is a strong electrolyte. It's a strong electrolyte, meaning that when I put it in water, I'm going to make all sodium and all acetate. It's going to go 100% go that way. And when we see group 1 metals that are cations, they do that. So sodium, potassium, lithium always break 100% apart in water. So if I put some sodium acetate into my acetic acid solution, I'm going to take my acetic acid solution, which was at equilibrium, and I'm going to add a bunch of acetate, which is a product. Now this is going to, via Le Chatelier's principle, shift my reaction that way towards the reactants. So I'm going to make even less hydrogen ion than I had before. So if I have less hydrogen ions, that means that my pH goes up. I increase my pH by adding the common ion, acetate. So whenever I have a weak electrolyte, and then I put a strong electrolyte in there in a solution that has one of the common ions of my weak electrolyte, then my weak electrolyte ionizes less than it would on its own. So we're going to have that shift, and that's due to Le Chatelier's principle. That affects acid-base equilibria and also affects solubility, which we'll talk about at the end of the chapter. So how do we do this? We set things up the same as we would before. If I want to find the pH, so that's related to the hydronium concentration, okay, of a solution that has 0.3 moles of acetic acid and 0.3 moles of sodium acetate. So we're first going to write our dissociation of acetic acid, which is HC2H3O2 in water. Okay, I'm just adding, and then I'm going to dissociate into hydronium and acetate. So same thing we did before. The only caveat now is my initial amounts are not always going to be 0 of my product. So the second step, which I have here, I'm going to actually write over here, is to write our equilibrium expression. So I'm going to do my Ka for acetic acid, products over reactants, hydronium times acetate over acetic acid. Great. And now I'm going to do my ice table. That's step 3. So remember, I have concentrations for my K, right? In here, I'm in concentration of hydronium, concentration of acetate, concentration of acetic acid. So what I'm going to have to do is make sure I'm in concentration in my ice table. So I have 0.3 moles of acetic acid in 1 liter. So I have 0.3 molar. And then I also am adding 0.3 molar of sodium acetate, which is basically 0.3 moles of C2H3O2, since it's a strong electrolyte in 1 liter. So I have 0.3 molar here too. Now I didn't add any strong acid, which is a strong electrolyte form of hydronium, so that's 0. Now I'm still going to do minus X for my reactants, plus X for my products. So now I have 0.3 plus X for acetate. Now I want to find pH, so I want to find hydronium concentration. So I'm going to plug in my Ka for acetic acid, 1.8 times 10 to the negative 5, equals, now hydronium is X, now acetate is 0.3 plus X, and acetic acid is 0.3 minus X. So key thing here is I'm adding a common ion, so I'm going to actually be shifting my reactants that way. So we had our rule before that, if my Ka is about 1,000 times less than my initial concentration, I can make that approximation that gets rid of the minus X at the bottom. But now I can also, because I'm going to dissociate even less for this X here, since I have a common ion and via Le Chatelier's principle, I get to lower that expectation, that threshold. Either way, this still works for this case. But now what we get to do is, if your ratio of your initial concentration of your reactant over your K is greater than 100, not 1,000, then you get to make the approximation where you don't have, the X is so small that it's not going to impact it. So what I get to do here is do 1.8 times 10 to the negative 5 equals X times 0.3, get rid of the plus X, and on the denominator, 0.3, get rid of the minus X, and I can now solve for X this way. So the approximation is a little bit more able to be followed because we're lowering the limit, because our dissociation is going to be even less than it would on its own if I just had a weak electrolyte. Okay, so in this case, our concentrations are the same, so those two things cancel out. They won't always be the same. So we get X equals 1.8 times 10 to the negative 5, which is equal to hydronium concentration. So then if I take negative log of this, then that equals my pH. And so negative log of 1.8 times 10 to the negative 5 is 4.74. And if you go look at one of our previous slides, if I just had acetic acid without acetate there at all, my pH of just acid was 2.63. And by adding that amount of acetate, it went up to 4.74. So pretty big increase just by adding that electrolyte. Okay, weak bases work the same way. So if I have a weak base and I have a salt of its conjugate acid, then the base is going to dissociate much less. So it won't dissociate as much as it did if it was by itself. So for example, if I have ammonia and then I put like ammonium chloride or something in there, ammonium nitrate, then it's going to shift towards the reactant. So I'm going to have less hydroxide. So my pH is going to go down. Okay, so let's practice. Calculate the pH of a solution containing 0.085 molar nitrous acid and 0.1 molar potassium nitrite. So you should look at that group 1 and just cross it out. We don't care about that, but nitrite is part of my weak acid. So whatever your weak electrolyte is, or in this case weak acid or base, we're going to dissociate that. So I'll have nitrous acid in water to give me hydronium and nitrite. I'll write my Ka expression. It gives me a Ka value, so that's a good sign. That is products hydronium times nitrite over reactants, nitrous acid. Whoops. Okay, and so initially I have 0.085 molar of nitrous acid, and then I also have 0.1 molar of nitrite. No hydronium, so then I'm gonna lose some reactants. I'm gonna gain some products. So then when I plug this in, I have my Ka 4.5 times 10 to the negative 4 equals X times, now this is a common ion, so I get to get rid of that 0.1 and don't have to put the plus X. And then I'm going to put 0.085 on the denominator. So then I'm going to get X by itself, I'm going to divide by 0.1 to get rid of that, and times by 0.085. And so then I have X equals my hydronium concentration. And I end up getting, let's calculate it, 3.83 times 10 to the negative 4 molar. Now I could double check my percent ionization to make sure I could make that approximation. Remember, it's hydronium at equivalence divided by my initial acid times 100. So I'll take that 3.83 times 10 to the negative 4, divide by 0.085 times 100, and I get a 0.45%, so really low. So that was okay to make that approximation. Great. So then to find the pH, I'm going to do negative log of hydronium. So negative log of that value. Negative log of 3.83 times 10 to the negative 4 equals pH of 3.41. Okay, that's the process. Let's try it again. Calculate the fluoride ion concentration and pH of a solution that's 0.2 molar hydrofluoric acid and 0.1 molar hydrochloric acid. So we at first ask ourselves, what's our weak electrolyte? So our weak electrolyte is hydrofluoric acid. It's in water to make hydronium and fluoride. Now our Ka for this acid is products over reactants, hydronium times fluoride over hydrofluoric acid. Okay, so I have 0.2 molar initially of hydrofluoric acid. Now you may wonder, okay, I also have hydrochloric acid, but remember, my hydrochloric acid is a strong acid, so the concentration of hydrochloric acid equals the concentration of hydronium ion. Remember, it completely dissociates. So that's how much hydronium I have. And now in this case, I don't have any fluoride. So I'm now going to follow the same process, minus X plus X, 0.2 minus X, and then X, 0.1 plus X, and then X. So Ka, which is 6.8 times 10 to the negative 4. No, you do not need to memorize it, but I just happen to have the Ka of hydrofluoric acid memorized. So we're going to do 0.1 for hydronium. I'm going to get rid of the plus X because we have a common ion. Then I'm going to times it by X here, divided by 0.2 minus X, but I'm going to get, again, rid of minus X. So then I'm going to multiply up by 0.2 and divide by 0.1 to get rid of those. And I get X equals 1.36 times 10 to the negative 3 molar. And that's my fluoride concentration. Okay, notice hydronium is 0.1 plus that. Fluoride is X. So pay attention to what does X actually mean. Cool, that's what it asks, what the fluoride ion concentration. It also wants to know pH. So pH is a negative log of hydronium, which in this case is 0.1 plus the X. So we're going to do negative log of 0.1 plus the X, so 1.36 times 10 to the negative third. If you do this, you get 0.994. So pH equals 0.994. Now you could realize that this number here is so small compared to 0.1. And if we did make the approximation there and just did pH equals negative log of 0.1 and not do minus or plus X, then I would get 1.00, which is pretty close to that one. So you can even make the approximation there. In this last example, I want to find the formate ion concentration of a solution that is 0.05 molar formic acid and 0.1 molar nitric acid. So let's write in a different color. So I have formic acid, dissociate, here's B, HCOOH in water. It's going to produce formate and hydronium. And once again, I have my Ka hydronium times formate over formic acid. And it gives us that value, 1.8 times 10 to the negative 4 is a Ka. So now when I fill in my ice table, this is getting in the way. Let's do an ice table right here. Perfect. Okay, when I do my ice table, I have 0.05 molar formic acid, and then I don't have any formate. It doesn't say. It could have said I had like potassium formate, but I don't. I have nitric acid, so 0.1 molar. And remember, nitric acid is a strong acid, so that means that I know my hydronium concentration is 0.1 molar. So then once again I do minus X, and then I do plus X. So now I can solve for it. I get 0.1, I'm going to not do the plus X because of the approximation, X over 0.05 minus X, and don't worry about the minus X. So then I do my Ka times 0.05 divided by 0.1 to get rid of that guy, times by 0.05. And I get X, which is my formate ion. Oops. Is equal to 9.0 times 10 to the negative 5. So very small. This is a weaker acid. Well, it's pretty similar actually to the other one, but we have a lower concentration. So pretty small. So that's one of the answers. And then the other one is going to be the pH, which is the negative log of hydronium. So I can realize that hydronium is 0.1 plus that really small number, or I can just do negative log of, I can make the approximation 0.1. So I'd give a pH of 0. Now if I add that to 0.1 and take the negative log of that, then I get even closer. So negative log of 0.1 plus that X value is 0.9996, so even more of a reason to use the approximation. So why we talked about common ions is to lead into this topic of buffers. So when we have a solution that has a weak acid-base pair, so conjugate acid-base pair, right, they just differ by a proton, then they're really special because if we add strong acid or base to them, they resist big changes to the pH. So for example, if I put like a tiny little bit, like a drop of a strong acid into water, my pH is going to go from like 7 down to like 3. But if I have a buffer, I could put that amount of, that drop of acid in there, and it's not going to do anything to my pH. So it's pretty cool. To be a buffer, you have to have relatively high concentrations of your acid and base, so higher than 10 to the negative third molar, and they need to be pretty similar in concentration. So you can see this here. Here's a buffer solution where I have hydrofluoric acid and fluoride. There's my conjugate acid-base pair. They're relatively equal concentrations. If I add a little bit of strong acid, so hydronium, then it's going to react with the fluoride to produce a little extra hydrofluoric acid, and I'm going to lose some fluoride. But overall, after my hydrogen got added, I still have acid-base pair in a decent similar concentration. And my hydronium that I added is basically gone. And then if I add hydroxide, so over here, if I add some hydroxide, then it's going to react with my hydrofluoric acid to produce fluoride and water. So I have a little extra fluoride and a little less hydrofluoric acid, but my hydroxide basically gets used up, and it's not going to be around to impact my pH. So basically, that acid or base pair will neutralize one component of the buffer, so the pH doesn't change very much. How to make a buffer? This is going to be important. Pay attention. You could either mix some acid and base, a salt of its conjugate base together, like I showed you in the common ion example, right? If I have like this concentration of acid and then I just dump some acetate, for example, if it's acetic acid, then I have a buffer. Or I can partially neutralize a weak acid with a strong base, or vice versa with a weak base. So I can partially neutralize to get some acid left over and the conjugate base. So we'll show you that. So for example, if I have HA and I react it with hydroxide, I'm going to make the conjugate base in water. So I have, let's say I have 0.1 moles of, actually let's do 0.2 moles of my weak acid, and I use 0.1 mole of hydroxide. Then that means my hydroxide is going to go all the way away, going to be my limiting reactant. And I'm going to have at the end 0.1 molar of my base and 0.1 molar of my acid left over. So now I have an acid-base pair. I have a buffer. So there's a really cool equation we can use when we have a buffer. What we're going to do is we take our acid dissociation expression, Ka, and I'm going to take the negative log of both sides. So I get negative log of Ka equals negative log of hydronium here. And then I'm going to separate here. So when I separate, these two things are being multiplied by hydronium. So I can add the negative log of A minus over HA. So what I get here is negative log of Ka is called pKa equals negative log of hydronium is pH plus negative log of the base over the acid, conjugate base pair. So I'm going to move this guy to the other side by adding. So I end up getting pH equals pKa plus log of my conjugate base over my conjugate acid. Great. This is called the Henderson-Hasselbalch equation, and you can only use it when you have a buffer. So if you see buffer, you should immediately think of this equation, and it's going to make your life a lot easier. There is a base version. The base equivalent of pH is POH. The base equivalent of pKa is pKb. Whoops. And then the base equivalent of conjugate base is conjugate acid. So I'll have the conjugate acid form over the concentration of my base. So that is the base version of Henderson-Hasselbalch, but it's the same thing. So what's the pH of a buffer? Ding, 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 Henderson-Hasselbalch. That is 0.12 molar lactic acid, 0.1 molar sodium lactate, and here's the Ka. So I'm going to use my pH equation, Henderson-Hasselbalch. pH equals pKa, so negative log of the Ka, which is 1.4 times 10 to the negative 4, plus log of the conjugate base, so A minus is lactate here, 0.1 molar, over the acid, lactic acid, 0.12. So when I plug that in, I get my pH is 3.77. This is a cool equation because I'm able to basically make the approximations I would need to up here for my acid expression, but I get to do it kind of more directly, and I don't have to worry about, I don't really have to worry about an ice table or anything like that. So if you see a buffer, you get to use this and don't have to worry about your expression. But if you want to, you can still do it. So whatever you like. So let's do another one. pH of a buffer, that's 0.12 molar benzoic acid and 0.2 molar sodium benzoate. And keep in mind the Ka of benzoic acid is 6.5 times 10 to the negative 5. Okay, so I have a buffer. It has relatively high and similar concentrations. So I'm going to use my Henderson-Hasselbalch. pH equals pKa plus log of the base over the acid concentration. So I get negative log of Ka, 6.5 times 10 to the negative 5, plus log of my base, so benzoate, 0.2, over my acid, 0.12, and I get a value of 4.41 as my pH. Okay, here's an example of when Henderson-Hasselbalch might not work. So my approximation is not gonna hold up. So here we have a buffer. It has concentration 1 times 10 to the negative 3rd molar of acetic acid and 1 times 10 to the negative 4 molar of sodium acetate. So already we can see low concentrations of my acid and base pair. And also, they're not very similar. They're off by a factor of 10. That's not close in concentration. So let's do, we're going to use Henderson-Hasselbalch first. So we'll use pH equals pKa plus log of the base over the acid. And so my Ka of acetic acid, I'll do negative log of Ka, 1.8 times 10 to the negative 5, plus log of acetate, which is 1 times 10 to the negative 4, over 1 times 10 to the negative 3 for my acetic acid. Great. So this gives me an answer of 3.74. So that's what we would use with the Henderson-Hasselbalch equation. So realizing that this is an acid, so now we're going to do it the old-fashioned way, no approximations, common ion type style. I have acetic acid and water, makes acetate and hydronium. So I have acetic acid has 1 times 10 to the negative 3rd molar, acetate is 1 times 10 to the negative 4 molar, and no hydronium. And you can see those are really close to the Ka. So we're not able to make the approximation because my concentrations are very close to my Ka. So I'm going to add x to my products, minus x from my reactants, 1 times 10 to the negative 3rd, minus x, and then 1 times 10 to the negative 4, plus x, and x. So I'm going to plug that into my K expression, which is hydronium times acetate over acetic acid. So I have 1.8 times 10 to the negative 5 equals x times 1 times 10 to the negative 4 plus x, and then 1 times 10 to the negative 3 minus x. Okay, fun. So now we're going to multiply the denominator up. So I'm going to actually multiply this on both sides. So So multiply that up. So I'm going to have to do some distribution. So I'll have 1.8 times 10 to the negative 8 minus 1.8 times 10 to the negative 5x equals x. I'm going to actually distribute that in as well. Whoops. So I'm going to have, let me erase that. 1.1 times 10 to the negative 4x plus x squared. Okay, fun. So now we're going to, if I keep saying it's fun, then it will be fun, right? I'm going to put it all on the same side. So I'm going to move these guys over. I'm going to get x squared plus 1.18 times 10 to the negative 4x minus 1.8 times 10 to the negative 8 equals 0. Now I'm going to plug that into a quadratic formula calculator. And I'm not going to do it by hand because that sounds awful. So let's plug it into your quadratic formula calculator on your calculator or website. You get x equals 8.76 times 10 to the negative 5. And that x is hydronium. So if I take the negative log of this, I get my pH. My pH is 4.06. So you can see, making no approximations, that's always going to be the more accurate answer. I'm off by quite a bit from the approximation. So my approximation, I kind of assumed that I would be a lot more acidic than I am. So when you don't meet those criteria because you have your concentrations are not similar enough, they're off by at least a factor of 10, or they're very low, you need to make sure you do it the long, old-fashioned way. Okay, let's practice preparing a buffer. So how many moles of ammonium chloride must be added to 2 liters of a 0.1 molar ammonia solution to form a buffer with a pH of 9? Okay, so let's dry out the equation. So I have ammonia plus water to produce ammonium plus hydroxide. And this has a Kb expression. Since it's a base, it made hydroxide, so I'm going to have ammonium times hydroxide over ammonia times water, which is just 1, pure substance. Kb in this case is 1.8 times 10 to the negative 5. So I want to find out how much ammonium chloride. Now remember, this is a strong electrolyte. Think common ion. So I want to know how much of this I need to add. So let's find the initial concentration of ammonium I need to make. And now I know I have a 0.1 molar solution of ammonia. And I want to form a buffer whose pH is 9, which means that my pOH is 14 minus 9. So my pOH is 5. So if I want to find hydroxide's concentration, I'm going to undo that pOH, so it'll be 10 to the negative 5. So that's what I know my hydroxide is, 10 to the negative 5. I started at 0, so now I know my change. I need to add 10 to the negative 5 to my products. So I have x plus 10 to the negative 5. And then I'm going to subtract it from my reactants. So 0.1 minus 10 to the negative 5. Okay, great. I'm going to plug it into my expression. So I have 10 to the negative 5 times x plus 10 to the negative 5 over 0.1 minus 10 to the negative 5. Okay, so I can move this guy up and this guy down. I know that sounds confusing, but basically going to multiply 1.8 times 10 to the negative 5 times that denominator, 0.1 minus 10 to the negative 5, that's just a number. I'm going to divide by 10 to the negative 5, and that equals x minus 10 to the negative 5. So then I can add that little tiny number over 10 to the negative 5 plus that, and I can find x. So x in this case equals 0.18 molar. So that's my initial concentration of ammonium. So then if I want to find out how many moles I need to add, I'm going to realize that that's 0.18 moles per liter. So I'll multiply by the 2 liters I have, and I get 0.36 moles. So when you have a buffer, it can really only handle so much neutralization before it actually starts to raise it or starts to change the pH. So remember earlier with that example with the ethylene glycol turning into glycolic acid, and then if you drink enough antifreeze, then you can actually neutralize a lot of your bicarbonate ion in your body, which is part of that acid-base pair. And so if that's gone, then we won't have any additional base to react, and so any additional acid you have will really impact your body. So here we have, in general, right, if I use Henderson-Hasselbalch equation, I know that, pH equals, pKa, and this is especially good when your concentration of your weak acid is equal to the conjugate base. So you're right at that pKa. Your pH is sitting on the pKa. And this will be true, this will hold true when these two things are equal to each other, when your acid-base pair are equal. But if I have 1 molar of my acid-base pair versus 1 molar, my pH will still equal my pKa, but my 1 molar solution can just handle more neutralization. So I'm able to neutralize more strong acid or base before I can change the pH if I have a concentrated solution. So higher concentration for your buffer equals higher buffering capacity. So more neutralization can happen. And the best pH range, so that's why they say that you need to have like a high-ish concentration of your acid-base pair, because you're able to buffer for a lot longer. Also, one of the qualifications is that your concentrations of acids and base need to be within the same range, and that's so you're centered on that pKa. If one or the other is at least 10 times different from a different one, then your pH is going to change by a factor of 1. So for example, if I have acetic acid, its pKa is 4.74. So if I have a pH that's around 4.74, I'm in a good buffering area. If my pH drops to 3.74 or less, or higher than 5.74 for acetic acid, it's not able to buffer very well. And that's because my acid-base pair are too far apart, so I'm not buffering very well. So in general, when you have a buffer, it's going to neutralize some acid or base. So we're going to need to, the step is, take your strong acid or base and neutralize it. We want to do this in moles, and we want to basically react all of our acid or base need to react. So for example, if I have my weak acid and I add some hydroxide, I'm going to find out how many moles I have of each. So let's say it's 0.1 and 0.15, and I'm going to react all of it. So whoever's my limiting reactant, the smallest amount, that's how much I'm going to subtract from both sides. And that's how much I'm going to add to my products. So that's what I will do over there. So we're going to add our strong base, and then we're going to see what we're left with. So at the end, if I have acid-base pair left, then I have a buffer. So if I still meet buffer conditions, then I'm going to use Henderson-Hasselbalch to find the pH. If I don't, then I'll see what I have and I will adjust accordingly. Okay, so we have the same problem as before. And earlier in the chapter, we found out that our pH of this solution was 4.74. Great. So I have a buffer, and I'm going to add 0.02 moles of sodium hydroxide. So I need to realize, is sodium hydroxide it's a base, is it gonna react with my acid or my base in this conjugate acid-base pair in my buffer? base is going to react with the acid. So I'm going to have my acid. I'm going to neutralize it with my base and write my products. My products here are my proton's going to go to my base. So I'm going to make water and acetate. So I have 0.3 moles of this, and technically I also have 0.3 moles of my product. And I have 0.02 moles of my sodium hydroxide. So of my reactants, I'm going to, hydroxide is the limiting reactant, so I'm going to subtract 0.02 moles from each side. And I'm going to add that to my products. Oops, 0.2. So I have 0.32 moles. Now this is in 1 liter, so I'm going to divide by 1 liter. Now I can use Henderson-Hasselbalch. At the end here, so if this is ICE, my end, I have concentration of acid and concentration of conjugate base. So I have a buffer. So I could use pH equals pKa plus log of the base over the acid. So I do pKa is 4.74 plus log of my base, so 0.32, over my acid, 0.28. And I can see that my pH went up a little bit. It went up to, 4.80. So a tiny bit up, and I added a significant amount of moles of hydroxide, and my pH didn't change very much, so that's pretty cool. Okay, so let's see the difference if I have in pH, if I add 5 milliliters of a 4 molar sodium hydroxide solution to 1 liter of water, or to 1 liter of a buffer that has 3 molar of acetate and acetic acid. So for the first problem, either way, I need to know how many moles of acetate I am, or hydroxide I'm adding. So I'm going to do my 5 milliliters. I'm going to convert it into liters, and then use molarity, 4 moles per liter. So that gives me 0.02 moles of hydroxide. And we actually saw this in our last problem. So we saw if I add 4 moles, or 0.02 moles of hydroxide into my buffer, then my pH goes up to 4.8 from 4.74. So already I know this bottom one. Look at the last example. We calculated that. But if I put this into water, then I have 0.02 moles of hydroxide in 1.05 liters of water. 1 liter coming from the water and 5 milliliters coming from my hydroxide. So my concentration of hydroxide is 1.9 times 10 to the negative 2 molar. So then I can find pOH by doing negative log of hydroxide. Same stuff we've been doing. I get so my pOH is 1.72. So my pH equals 14 minus that. And I get 12.28. So my pH in neutral water goes from 7, I add that 5 milliliters, I go up to 12.3 basically, or 12.28. I have an increase of over 5 pH units. That's huge. Where if I add that same amount to my buffer, my pH barely changes. So let's see what happens with an acid. So if I add 0.02 moles of HCl is hydronium, or H plus ion. So I'm going to calculate the pH by adding that to water versus adding it to a buffer. So in my buffer, I had 0.3 moles of acetate and of acetic acid. So who's going to react with hydronium, the base or the acid? Well, hydronium is an acid, so my acetate will react. So I have H plus C2H3O2 goes to HCl C2H3O2. So I have 0.02 moles of that. I have 0.3 moles of acetate and 0.3 moles of acetic acid. So I'm going to neutralize, subtract over, and then I'm going to add 0.02 here. So now I don't have any hydronium, and I have 0.28 of acetate and 0.32 of acetic acid. So I could do my pH equals pKa plus log of the base over the acid, so A minus over HA. And that will equal 4.74 is my pKa of acetic acid, plus log of my base, 0.28, over my acid, 0.32. So I end up getting 4.74 plus log of 0.28 over 0.32 is 4.68. So barely a shift. Now if I take that 0.02 moles of H plus and I add it into 1 liter of water, my hydronium concentration is 0.02. So if I want to do pH, it'll be negative a log of 0.02 molar, and I get a pH of 1.70. So to go from neutral, 7.0, down to less than 2, that's a huge change. So buffers are awesome because they really keep that pH really stable.